Hi, everyone. In this video, I wanted to show you a workflow that I have received a lot of requests for, which is basically how can we use toplogicpy to derive building engineering model or building energy models, excuse me, BEM, from disjointed rooms that may have come from Revit or other places. So I wanted to show you one possible workflow, one possible solution. Obviously, there is no such thing as a perfect 100% solution that applies to everything. There will always be edge cases that would not work. But I believe this workflow is robust enough, at least for more orthogonal buildings, more kind of like a simpler type of layout. But try it and let me know. And if you have any way we can enhance it, improve its performance, also please share that with the whole community. I also want to mention that this workflow depends on the latest toplogicpy version, which is now 0.8.9 as the recording of this video, but obviously I'm working on it continuously and you might get a newer version when you test it. Okay, so what is the goal? The goal, as I said, is to convert disjointed spaces, as you can see here on the left side, that may have come from Revit or other pieces of software, to something that is clean, where all the surfaces match, so that you can build a building energy model that is compatible with software like Energy Plus and Open Studio or Ladybug, Honeybee, etc., which also use Energy Plus. And as you can see on the right side, we have built what we call in toplogicpy a cell complex, and we derived the graph of that cell complex. So you can see that the graph, which are these black dots and edges in the middle of this building, are completely connected. So toplogicpy now understands the adjacencies between them, and therefore we can also compute the shared surfaces between each of these spaces. I tried to model something that is a little bit more complex than just a simple kind of segmented box. And if you really look closely on the left side, you'll notice that there are different gaps between the solids. So, for example, this one here has a larger gap than the one here. Obviously, this roof pokes a little bit more, and they are also they have gaps in all directions, in the X, Y, and the Z. So even the floor slabs are not there. They have created a gap. So hopefully we can show you how to combine all of this into a clean cell complex. I also, added some inclined roofs in order to show that does not affect anything. It's just not made for only boxes. And obviously this large space here is an L shape, and that also does not cause any problems for this workflow. So what is the what is the methodology that you need to follow? And the trick here, and what the kind of preparatory work that you need to do, is you need to agree on an XYZ grid. Basically, you can say on the x-axis, I have these grids, let's say as you can see here, at 0, at 3.5, at 10, at 20, and at 40. So you place a grid. And most projects that are coming in from Revit would have that grid already. But you need to see if there are any notches or kind of additional significant values on the x-axis that need to be added to this grid. So you just need to kind of decide on what is the main spacing that you want, what are the significant things, and it will snap all the vertices to these grids. So you can have a different grid on the x-axis, a different one on the y, and a different one on the z. As you can see here, for example, for the z, we decided to do it by 3 meter floor height, floor to ceiling height, so 0, 3, 6, and 9. And the ones on the x-axis are different than the ones on the y-axis. Once you have created this grid, you use something called vertex.align coordinates in toplogicpy to align the coordinates of all the vertices, as I said, with a user-specified X, Y, and Z tolerances. So those tolerances can also be different for the x-axis, the y-axis, and the z-axis. So those are called x epsilon, y epsilon, and z epsilon. And you can therefore manage the process so that you snap these points in a more controlled manner. But the idea here is that if you have a vertex, as you can see here on the left side, with coordinates 3.48, for example, 10.02, and 5.92, given these numbers here for the grids, this would be converted for you to 3.5, 10, and 6. Now, we avoid issues of non-coplanarity of vertices simply because everything is going to be snapped to the same plane, so it kind of forces it to remain planar, so that avoids that problem that you would have otherwise. So then the next step is just simply to replace all vertices. So we have in toplogicpy a method called topology.replace vertices, and you give it the vertices of the first cell, for example, and you replace them, and it will go ahead and replace those vertices for you. Once you have those replaced, you can rebuild the cell, and then from there you can say cell complex dot by cells, and it builds you the cell complex and gives you that graph as we can see here. And I'll show you that live. So let's go ahead and take a look at it live. This Jupyter notebook is on GitHub, so I'm gonna just simply restart and run it one more time. So the first step always is to import libraries. You don't need those first two lines. As always, this is just because I'm working on my development machine, but we import some things here. I'm gonna import one more library or class, which is the face, toplogicpy.face, import face. And we run the first cell. And it will tell me that my version, if you type if you print helper.version, excuse me, it will tell you that you are using 0.89, which is the latest version available on PyPy. If it is not, please go ahead and upgrade using pip install toplogicpy -- upgrade. So this cell basically, instead of importing geometry from somewhere else, you could, by the way, of course. I decided just to build it here so that you don't have to worry about building a model yourself if you don't have a model ready to go. But what you really need to do is replace that with your own model in order to do some testing. But this is the model that is not cleanly modeled. So let's go ahead and take a look at what it looks like. So it looks like this. And let me just zoom in so that you can see the problems. This is a bigger gap than this one. There are gaps almost everywhere that you can see here, as well as lines that go through two faces like this. And you can see that there are gaps everywhere. It's completely disjointed. And you can even see here, this is higher than this one. That all does not matter. That will all be fixed. So this is the geometry. These are called spaces. As you can see here, it's a list of cells. So here we decide on the grids. So we have decided that on the x-axis, we want to restrict everything to either 0, 3.5, 10, 20, or 40. And on the y-axis, we want to restrict it to 0, 10, 20, and 30. And on the z-axis, we want to restrict it to 0, 3, 6, and 9. And therefore, we have now a new empty list of new spaces that we're going to fill with these fixed spaces. And we loop through every space in the spaces here for space and spaces. We get its vertices, so topology.vertices of that particular space. And then we initialize a new list of vertices that we are going to populate with these corrected vertices. And then we loop through every vertex in this space, so for V in vertices. And then the new vertex is basically vertex.align coordinates. That's the method that you would call. You give it the vertex, you give it the X list from here, the grids that you have, the Y list and the Z list. And then you tell it on the X axis, what is my tolerance? What do I use as the smallest distance? If it is within that tolerance, less than this tolerance, it will snap it to the closest match in that list. Same thing for Y and same thing for Z. And you can see here that X is different than Y and Z. Once you have this new vertex, we assign it to, or we append it to the list of new vertices. And then all we need to do here is call topology.replace vertices. We give it the original space. We give it the original list of vertices, that's called vertices A, the new list of vertices, which is vertices B. It will make a cluster of faces. We feed that into topology.self-merge, which merges it into a cell. And that becomes your new space. It's a new cell. And then basically we take that and append it to the list of new spaces. And then once we have these list of new spaces, which are all cells, hopefully, you can create a cell complex by cells. You give it the list of spaces. And then we created a graph just so that to show you that it is indeed a cell complex and everything is connected. In this case, I'm saying don't connect the spaces directly. However, do connect them if they share a topology, if they share a face, basically. So let's go ahead and run this. It's very quick, as you can see here, 0.7 seconds. And it created a very clean cell complex. All the faces are matching. No problems at all. Even this one has been extended. If you compare it, for example, to what is going on here with this wedge falling a bit short of the space underneath it. But because this is within the tolerance, it pushed it out so that it matches completely and it gives you a clean model all the way through and a clean topology, clean graph. All right, so now what can we do? Now what we are able to do here, this is just to kind of show that you can get the shared faces. Basically, I'm getting, again, the cells of the cell complex. Don't worry so much about this. Basically, I'm going through the cells for the same cells, basically, comparing each one to the other one, making sure that I don't compare a cell to itself. And also, if I compared, cell 1 to cell 2, I don't need to compare cell 2 to cell 1. So I put ij in visited. This is just to kind of make sure I am more efficient in this nested loop. And then I get the shared topologies. And I am interested in the shared faces. So I get the faces out of those shared topologies. And then if it is more than 0, if they share a face, I basically compute the total area. So total area plus equals face.area shared space. So I'm just simply adding up all the shared faces, all the areas of the shared faces, and then I'm simply adding them up. And I am also showing visually the shared faces, the edges of A, the edges of B, just simply to highlight the shared faces in red. And I will show you what that looks like. Otherwise, I just show two cells that have no shared faces between them. And I also even print the cells, the cell numbers, and how many square meters do they share between them. As you can see here, this is the output here. So, this is wrong here. So let me run this one more time. And it will open up the browsers, because I'm sending them to the browser so that I can show them to you one by one. All right, so let's take a look here. These are two cells that share this face, these share these faces, etc., etc. So you can see that it does this comparison correctly, and so on and so forth. And that's it, really. As I said, this is on GitHub, so give it a try and let me know how it works for you. And I hope you found this useful. Thank you.